So this is the sort of the reading 2, which talks mainly about refracted light. So that was as it goes between one material to another, the light refracts. A light travels in air and approaches a flat glass block at some angle relative to the normal, perpendicular to the surface. After entering the glass, the light rays wavelength becomes larger and it bends towards the normal, wavelength becomes larger and it bends away from the normal, and so on. And the idea is that since you know as it goes into the glass, now at this point, that the index of refraction is larger than 1, which means that the speed of light in the glass is less than 1. Since the velocity is less, that means the wavelength becomes smaller. But as it also bends towards the normal. So let's talk about this a bit again. So you have a light ray which is coming in at some angle. And again, remember, all the light rays always are measured relative to the normal. And so when it refracts, going from, say, air to glass, air has an index of 1. Glass has an index of usually around 1.5. And so the refracted angle is always less than the incident angle if I go in this particular direction. So in other words, n1 sine theta 1 is equal to n2 sine theta 2. So in this case, basically you have 1 times the sine of the incident angle, and you have the glass and also basically the refracted angle. And again, since for any material the index goes up, that means that the angle has to decrease, and so it bends towards the normal. And again, the idea is that since the index of refraction in the glass is larger than 1, that means that the velocity in the glass is less than the speed of light, as it normally is. And so since v is equal to f lambda, if the velocity decreases, then the lambda decreases. So the wavelength becomes smaller, and it also bends towards the normal. Now, of course, the other case where you essentially go inside, you are incident from the glass block and go into the air, the reverse happens. So in this case, let's invert it. Then if you go between glass and air, then, and let's say this is the normal, as it comes in at some incident angle, then actually when it gets into the air, the angle increases, because essentially it's going from a higher index of refraction to a lower index of refraction. And so, and in particular, since the velocity increases, the wavelength increases, kind of in reverse. So the velocity here is less than the speed of light. Here, the velocity is equal to the speed of light in the air. So if I go into here, then essentially as it goes into the air, the wavelength becomes larger, and it bends away from the normal. You can see that also here with the simulation is if I change it, go back in here, let's basically make it so it goes from glass into air. Then what you'll notice is that the refracted beam is bending away from the normal. So in other words, if this one's about 20 degrees here, the incident angle is 20 degrees, then the refracted angle is about 30 degrees for this glass, which has an index of refraction of 1.5. Always the reflected beam comes back at the same angle. And so even if you're going from inside the glass to the air, then there's always some reflected light and some transmitted light. Then furthermore, the idea is that since the velocity is smaller in the glass, the wavelength is smaller, and so when it goes into the air, the wavelength actually gets larger. Which you can see here, these sort of show the wavefronts as they propagate towards the interface, and then they bend away from the interface, and the wavelength gets larger, and the speed of light basically becomes larger in the air. This one is what's talking about dispersion. And the issue here is that in air, or in a vacuum, C is equal to F lambda. And in fact, basically in air or in vacuum, light behaves exactly like sound waves, in that the speed of light doesn't depend on the frequency or the wavelength. So if you go from red light to blue light, then the speed of light is always the same. But in a material, then what happens is that the speed of light actually depends on the wavelength. This is why when you go into a prism, it disperses into different wavelengths. Usually what happens is that the speed of light basically gets smaller. So V gets smaller as lambda goes to the blue. So in other words, red light travels faster, blue light travels slower. And what that means is that the index of blue light is greater than the index of red light. And so if you were to look at this, say if you go across this interface, then because the index of blue light is larger than the index of red light, then blue light will bend more than red light. So in other words, suppose that I had, and I'm exaggerating here immensely, but let's suppose that this is blue light, and then it refracts. If I came in with a made it red, and so I come in with red light basically at exactly the same angle, then if I exaggerate it, the idea is that red light will essentially get this bend less, and actually it's still bending towards the normal because it's refracting. The speed of light in glass is less. But the idea is that blue light will bend more than red light. And so if you go into a prism, then the idea is that it will bend. And if I were to basically change the light from blue to red, what you notice is that blue light bends more than red light. This one actually is refracting twice. It gives you a rather larger effect. And so if I bend it, see, I could make it pretty large. If I go from red to blue, it can actually bend quite a bit. So what you notice is that blue light will get dispersed more than red light as you go through it. And this is why if you have multiple colors, then you can get essentially it will disperse into its colors, which of course you've seen before. So if you have a red and a blue laser beam incident at 45 degrees angle, upon entering the glass block, the blue light bends more towards the normal than the red light, because the index of refraction for blue light is larger than for red light. This is what's called dispersion. Okay, the last piece that we're going to talk about is total internal reflection. And the idea is what we've known so far is if you go from a glass into air, then the angle of refraction actually bends away from the normal, so it basically comes out more. But the idea is if I get it really, if I increase the angle of the incident angle, then the angle of refraction actually increases correspondingly. And eventually what you get to the point is where the refracted beam is just sort of grazing along the surface of the interface. And eventually what happens is that it can't get larger than 90 degrees, and so at the critical angle, essentially all of the light is reflected, none of it gets transmitted. And this is what's called the critical angle. So if I were to sort of look at this interface, and again, everything's measured relative to the normal. If you have an incident beam that essentially is coming in exactly at the critical angle, then the refracted beam is coming in at 90 degrees. And so, again, this can only occur if you're going from some index which is larger than 1, from a larger index to a smaller index. And so let's suppose that this is glass and this is air. Then what I end up getting is n glass times sine theta critical is equal to 1 times sine of 90 degrees, but this is equal to 1. So that sine of the critical angle is just 1 over n glass. And so, since glass is usually 1.5, if I take the inverse of that as 0.667, and then the inverse of the sine, and it gives you about 41.8 degrees is the critical angle, or about 42 degrees. And this is actually what you get here, is that if I look at this, once I'm slightly larger than if it's less than 42 degrees, then some of the power gets transmitted. If it's less than 42 degrees, all of it gets reflected. And exactly at the critical angle, basically, it's all reflected. So you get total, and this is what's called total internal reflection. Now the issue is suppose that the index, so in other words, if the index is around 1.5, then theta critical is about 42. But let's suppose that the index increased to about 1.6. Then theta critical, so if it was 1.6 and I take the inverse and then the inverse sine, then it's about 38.6 degrees, or about 39 degrees. So what it amounts to is if you, say, used blue light, remember that the index for blue light, because of this dispersion, is larger than the index for red light. If you set it at the critical angle for blue light, which is about 39, let's say suppose it was 39 degrees, for example, then for red light it basically would not be a large enough incident angle, and so some of the light would actually get refracted going into the air. And so if you're at theta critical for blue light, then for red light, some of it will get transmitted. So in the end, what it means is that it's partially reflected internally, and some of the laser power exits the glass block very close to the plane of the surface. Now the other one's partially reflected internally, and some of the power index exits the glass block very close to the normal to the surface. It's basically grazing the surface.